Well, welcome back. We are going to talk today about inference with means. So dealing with numerical data when we're finding the average. So we're going to talk about confidence intervals, how to estimate a population mean using a sample mean, and then we'll talk about hypothesis tests for a sample mean. So remember our steps for any kind of inference procedure. This is from our last unit. We're going to first start with stating, defining our parameter, and if needed, write hypothesis statements. We're going to plan by naming the interval or test that we're doing and then checking conditions. We're going to calculate our interval or the z-score and p-value. So interval for an interval, z-score, p-value would be for a test. And then we'll conclude, which is interpreting the interval or writing a conclusion to our hypothesis test. So those are our 4 steps. In the kind of intro lesson, we talked a little bit about conditions for these 2 examples that we're going to do. So I'm going to kind of go through those quickly, just so we can get through the actual math part. So this one has a research study that found that in a random sample of 1,520 American adults, the average number of books read in the last year was 12 books, with a standard deviation of 18 books. We're going to construct and interpret a 95% confidence interval for the mean number of books read by all American adults in the last year. So we're using the sample data to estimate what is true about the population. So again, we start by defining our parameter. So in this case, mu is our parameter because we're talking about a mean. Mu equals the mean number of books read in the last year for all American adults. Our conditions that we talked about already, we were given a random sample of adults. We can assume that 1,520 is less than 10% of all American adults. And our sample size of 1520 is definitely greater than 30. So that means that we are allowed to use a normal model because we know our sampling distribution would be roughly normal with that big of a sample size. Remember that it is okay on a free response question to not write out the formula as long as you name the test or interval or whatever that you're doing. So we're doing a 1 sample t interval for a mean on this example. I would caution you 1 sample intervals or 1 sample stuff. I would definitely be a little bit more comfortable with the formulas because those tend to show up on multiple choice a lot more often. And then it's always good to write it out if you know it on a free response because sometimes on AP exam, they want you to write it out. So it's good to be in the habit of writing it out. So on our example, we're going to do our actual calculate step. So just as a side note, this is our interval formula. We have our statistic, which is an X bar or sample mean, which would be 12, plus minus T star. If you saw in the intro video or intro lesson, we talked a little bit about T and why we use T instead of Z on a means problem. But this would be a T star. And then times S over square root of n. S is the standard deviation for the sample, and then n is our sample size. So if I fill in the stuff that I know, 12 would be my sample mean. My t-star is 1.962. We can get that from either the t-table or from your calculator. If you want a recap or reminder of how you can use your calculator, definitely let me know. But you can also get this from your t-table pretty easily. And then if I plug in S is 18, that's the standard deviation of the sample, divided by square root of our sample size. So 1520. Do a little bit of math, we get our interval 11.09 to 12.91. Again, if I put this in my calculator, I could go to stat tests and then I would choose T interval. So it does not call it a 1 samp T interval, but that is what it is. It just calls it regular T interval. We're using that one and not 2 samp T interval. We're also not using Z interval. We're always going to use T for means because we are pretty much always going to only know the sample standard deviation. The only reason we would use Z is if we knew the population standard deviation. So I'm using T. In this case, I'm going to use stats. That basically means that I know the statistics from this data. I know the mean and the standard deviation. I don't know the actual data itself. So if I actually knew the data for these 1520 American adults that I could put in my calculator, then I would do that. but in this case, I know the statistics, so I'm going to use stats. So X bar is the sample mean, which is 12. SX is the sample standard deviation, which is 18. N is the sample size, which is 1520. And we are doing a 95% interval, so I'm going to leave that at 0.95. And then there is my interval from the calculator. Okay. So there's the steps for that. Okay. So then we would interpret, this is our fourth step, so very similar to how we interpreted intervals for a proportion, but we're just doing it for a mean. So we're 95% confident that the true average or true mean number of books read in the last year by all American adults is between 11.09 and 12.91. Or we're 95% confident that for all Americans, they have on average read between 11.09 and 12.91 books in the last year. So now let's look at an example where instead of the actual statistics, they give us the data. So this one's talking about the level of dissolved oxygen in a stream or river. We want evidence that the average level of oxygen for like the entire river or the entire stream is at risk, which would basically mean it's below 5 milligrams per liter, I think. So we've got all these numbers, and that is our sample. And then we're going to do a hypothesis test. This would be a one sample t-test. So again, my first couple of steps, mu equals the mean dissolved oxygen level for all water in the stream. My null hypothesis is that mu equals 5. My alternate, what I'm trying to show is that it's at risk, which would be that mu is less than 5. So in this example, I started with the alternate because that's what I knew I was trying to find evidence for. And then my null hypothesis I knew needed to be the same number with an equal sign. So that's what I did there. Conditions, right? We were given a random selection of locations along the stream. They told us that. We're going to assume that 15 is less than 10% of all stream samples of that specific size in the river, in the stream. And then for our third condition, my sample size is not big enough. I only have 15. I don't know anything about the population. So this is one where I need to graph, and you can do a graph either as a dot plot on a sheet of paper, or you can do a graph on your calculator. If you put all this data in stat and then edit, we can graph the data on our calculator. There are instructions for that. We talked about it in the intro lesson, but it should be in the intro lesson video if you weren't here, where we talked about how we can do this on our calculator. But if I do it on the calculator, I still need to kind of sketch it on a piece of paper just so I can show. And I would say something like this: the sample graph of dissolved oxygen levels doesn't have any major skew or outliers, so we can assume the population is roughly normal. All right, so now we have our formula. Again, I'm going to look a little bit at the formulas, but just know that as long as you write the name of the test, this is a one sample t-test, then we can skip the formula, but it's good to be aware of it. So our formula would be our X bar, sample statistics, minus the mean from the null hypothesis, divided by my standard error, which is S over square root of N. So X bar from this set of data, and actually I'm going to pause for a second. All right, I got a little ahead of myself. So what I did in that pause was I went in and I went to stat and then edit on my calculator, and then I typed in all of those numbers under L1. Right, so if I were doing my formula by hand, the way I would get my sample mean and my sample standard deviation is one of two ways. The first way would be, again, type my data in there, go to stat, calc, one bar stats, tell it to use L1, leave frequency list empty, and then calculate. Right, and it would give me my sample mean, which is 4.77, so that's where I got this number from. And then it would also give me my sample standard deviation, which is 0.9395. So that's what I'm going to use on the bottom of the fraction. I'll come back to you in a minute where I could find that information the second way. So hold on. So back to my formula. So 4.77 minus the mu is from the null hypothesis. So originally our null is that mu equals 5. And then on the bottom, we have S, which again comes from the sample. So standard deviation was 0.939, somewhere in there, 94-ish, divided by the square root of N. So our sample size was 15. So that's where this number came from. If I actually put this in my calculator as a fraction, I would get negative 0.94 as my t-score. But I'm going to do it in my calculator because, yes, I can use the t-table to estimate a p-value for this t-score, but it's a lot quicker and a lot more exact if I use my calculator. So it's good on this type of thing to just use the calculator. So once I have my data in, so again, my first step would be to go to stat edit and put my data in there. I've already done that. I'm going to go to stat test, and then this is a t-test. So again, the calculator doesn't call it a one sample t-test or one samp t-test. It just calls it a t-test. So I'm using t-test, not two sample t-test, not z-test, because I'm doing a t. So this time I actually have my data, right? So I'm going to go to data. Mu0 is my null hypothesis, which was 5. And then it's asking for what list is your data in. So my data is in L1. If I needed to change that, I could push second 2 to make it L2, etc. But I'm going to make mine L1. And then we want to show that the oxygen levels are below, because we want to see if there's evidence that they're at risk. So I'm going to pick the less than. And then again, I can pick calculate or draw. Either one is fine. If I click calculate, it actually gives me the X bar and the standard deviation as part of the output. If I choose draw, it'll show me the graph and it'll show me what's shaded, but it doesn't give me those extra pieces. So that's another way that we can get that data. If I needed to write out the formula, I could just run the test and it'll give me that data. So I can see here my t-score is negative 0.94, just like we said. But now we also have a p-value, 0.1809 is my p-value. And again, if I had chosen draw on that option, it would have given me this graph. And there's my p-value. So now we write a conclusion, just like we always have. Same rules apply. Since our p-value 0.1809 is greater than the alpha of 0.05, we fail to reject the null hypothesis, which means there is not evidence of our alternate. There's not evidence that the average dissolved oxygen level in the stream is below 5 milligrams per liter. So we do not have evidence that aquatic life is at risk, according to our data. So that is how we do it when we actually have data. So my last little bit of this lesson is going to be to talk about how we find necessary sample size. So if you remember back when we talked about proportions, when we were doing an interval, we talked about this back then, where we knew what confidence level we wanted and we knew what we wanted that margin of error to be, but we didn't necessarily know what sample size to take. So it's a similar thing here. So we want to estimate the mean number or mean amount of money spent on prom by McNeil High School students with a 90% confidence interval. We plan on taking a sample of students who attended last year's prom, and we have a pretty good idea from previous data that the standard deviation of the money spent is about $45. If we want the margin of error to be no more than $10, how many students should you survey? So our margin of error formula for a means problem would technically be, it's everything that comes after the plus minus. So it's the critical value, so T star, times the standard error, which is S, or standard deviation, divided by square root of n. Now here's where the problem is. T star, if you remember in our discussion about the T star is different based on what your degrees of freedom is, and degrees of freedom is based on sample size. So there's actually no way for me to figure out what T star should be if I don't know my sample size. And I don't know my sample size because I haven't taken the sample yet, because I don't know what size the sample should be. So that makes this a little bit tricky, right? In order to actually use this formula, I would need to know the sample size, which kind of just defeats the purpose of the whole thing. So what we do for this scenario, because again, we're just estimating what sample size we should take, is that we're going to go ahead and for this kind of situation only, we're going to use a z-star. What that means is that the standard deviation that we're using should be at least a good estimate for the standard deviation for the population. So that's why this thing says that we have a good idea that the standard deviation is 45. Purely guessing here, but kind of have to assume that that's true for the population because we're going to use the z. So now we go ahead and plug in stuff we know. right? So we know we want our margin of error to be no more than 10. I know a Z star for a 90% confidence interval is 1.645. So again, I could use inverse norm to figure that out on my calculator. I could also use a Z table or even a T table to find that number. And then 45 was our standard deviation from previous years. We plugged that in. So at this point, it's algebra. A couple of things, I could divide by 1.645. So I have this as a lovely fraction. And now we've basically got a fraction equal to a fraction. And this is where we can do a little magic cross multiply, set them equal to each other. So that's what I did on this step. I cross multiplied 10 times square root of n. So 10 times square root of n on this side equals 45 times 1.645. Then we're going to divide by 10 so that I can get that square root of n by itself. And then lastly, I can square both sides to get the n by itself. And then this is what I'm putting in my calculator. So 45 times 1.645 divided by 10 squared. So if I do that, times 1.645 divided by 10, close parentheses, squared, I get a value of 54.797. And then that brings us back to, if you remember when we did this with proportions, we talked about 54.8 is what I would need, but I can't survey 0.8 of a person. And 54 might not be quite enough. So I always want to go up. So I'm going to say 55 students. And if I had a multiple choice question where my options were 50, 60, 70, 80, I always want to go up to the next higher option. Okay. Just one more example of this, just to show you in another situation. So this time we want to estimate the mean SAT score for students in McNeil, the 98% confidence interval. We want, or it says the standard deviation for scores of all McNeil students is thought to be 195. So again, that's our estimate we're saying for the true population standard deviation. So we're going to have to use Z. We want the margin of error to be no more than 25. So I plug everything in. 25 is the margin of error that I want. Our Z star for 98% confidence is 2.326. And 195 is our standard deviation. We're solving for n. Do all the math. Do the math. Do the math. So we end up with 2.326 times 195 divided by 25 equals square root of n. And then we square both sides. You get 329.2. And again, we're always going to round up. So that is how we do a sample size question. And that is it for this lesson. So we'll talk next class after spring break about all of this stuff a little bit more. See y'all later.